Ui, well, that's the way we say hello in Brazil. Hello, children. How are you people doing? I'm Saurabhkumardutt, and I'm here to teach you people a little bit of mathematics. Now, children, this magnificent place that you get to see is actually the Itamambuca beach, which is in Sao Paulo, Brazil. It's an awesome place to be in because here you get to be walking in serenity in the empty beaches, be always surrounded by the Atlantic green forests and mountains, surf like a pro, or probably take a swim in the Ubatuba River. Make sure, guys, you visit this place and have great fun here. I'm sure you will like to come back to this place. But all the people of Brazil that you go and meet there, do say to them, Ui. In this note, children, we'll be starting off this topic of the principle of mathematical induction, where initially I'll give you a briefing about the 3 quintessential steps which are required to crack any sum which is to be a proving of a mathematical identity which is given to you. After we are done with the basic steps, then I have a stunning sum waiting for you. Give it a try by pausing the lecture. If somehow you're able to do it, then a thumbs up to you, and if not, I'll be waiting there to explain the sum thoroughly to you people. So make sure, guys, you make the most of this lecture by watching this lecture till the last and become a perfect person who is given any question and is able to crack it when it's the questions on the principle of mathematical induction. So guys, let's start this lecture. First, I tell you people about the basic concept which is there in the principle of mathematical induction. For that matter, let's say we have a question like, we have say some 1 square plus 2 square plus 3 square, and all of that say continues up to some n square, which is equal to n times of n plus 1 times of 2n plus 1 divided by 6 is a mathematical identity. Right now, in order to prove this, you have to go through 3 steps. The first step is the basic step, right? And when we talk about this basic step, we here keep one term from the left hand side, and on the right hand side, in place of n, you have to substitute 1, right? That means you have to prove 1 square, which is the first term, to be equal to 1 times of 1 plus 1 times of 2 times of 1 plus 1 upon 6, right? And calculate and show that both of these sides are the same. Next, guys, after this, we have the second step where we talk about this to be the induction step. In the induction step, we take the value of this n, which can be from the set of integers, to be say some m, and we consider the statement which is Pm to be true. Right, and this is what the induction step is. That is, we consider the statement Pm to be true, right? And after we do this, then we come over to the third step, which is we talk about proving Pm plus 1. That is, in place of n, we substitute m plus 1, and we prove the statement using the last step, that is the induction step, right? So this is the proving step, which is the third step, right? And here you have to prove the statement which is Pm plus 1, right, guys? So this is all about sums in the principle of mathematical induction. So I'll just quickly discuss this with you people, and after that, guys, we'll be discussing the sum that I talked to you people about. So here, let's say we have 1 square plus 2 square plus 3 square and so on, that continues up to n square. For that matter, if you talk about this, this, guys, is known as sigma n square, right? And this is equal to n times of n plus 1 times of n multiplied by 2 plus 1 divided by 6, right? This is a statement which in times to come you will be learning in miscellaneous series of sequence and series chapter. And now, if this is a question which has been given to you to prove, right, what you do is you talk about first the basic step, where what you do is you put on the left hand side the first term only, and on the right hand side, in place of n, you substitute 1, right? So you talk about that to be 1 times of 1 plus 1 times of 2 times of 1 plus 1, which is divided by 6, right? So as on the left hand side, you're just talking about just picking up the first term, so that's going to be equal to 1 square, right? And here you got to show that 1 square comes to this statement P1, which should also give you 1 times of 1 plus 1 times of 2 times of 1 plus 1 upon 6. And if both the sides come to be equal, you will say that the basic step is done, and thus P1 is true. After that, guys, we come over to the induction step, where we talk about taking Pm to be true. That is, on the left hand side we pick up m terms, and on the right hand side, in place of n, we substitute m, right? And then we consider it to be true. After that, we come to the third step, which is the quintessential step, where what we do is, after writing the first m terms, we also write one more term, that is the m plus 1th term. And on the right hand side, in place of n, we substitute m plus 1, and then further we are able to get the value of this as the statement Pm plus 1, and using the last step, we prove this step also. So this is how we do the sums of the principle of mathematical induction. So this was a dry run. Now, guys, I have a sum for you people. So this is that question. Everybody give it a quick try by pausing the lecture for a little while, and after you have done a good endeavor, if you cracked it, then a thumbs up from my side, and if not, I am here to help you people out, right? So give it a try, guys. Okay, guys, now let's discuss the sum out, thinking this that you people have given it a valiant try. Now first, as I discussed, we will be talking about the basic step, right? So here, as this is a different type of a sum, so what you just require to do is, in place of n, just substitute 1, and that will then become your P1, right? So here we are going to talk about P1, where what you do is, in place of n, just substitute 1. As such, you will have 2 times of 7 raised to the power 1 plus 3 times of 5 raised to the power 1 minus 5, right? And now, guys, if we calculate this further, this will become 2, which is to be multiplied by 7, to which is to be added 3 multiplied by 5, and from which 5 is to be subtracted. Now, guys, next, when we calculate this, this comes to 14 plus 15 minus 5. As such, that becomes equal to 24, right? And since here in the question we have this, that you have to prove by the principle of mathematical induction, 2 times of 7 raised to the power n plus 3 times of 3 into 5 raised to the power n minus 5 is to be divisible by 24, right? So we find that as this is 24, so dividing this by 24 won't give us any remainder, and that is how you check whether a number is a multiple of a given number or not, right? So therefore here we will be able to say that P1 is true, right? So that's the first step, and I'm sure all of you people must have been able to do this step. After this, guys, we will be talking about the next step, that is, we'll be talking about the induction step, right? So in the second step, which is your induction step, you will be writing as under, that is, you'll be saying let Pm be true, right? And I'm sure you guys are going to be fascinated by this step, because it is just like having a magic wand in your hand and say that, let's say this is proved, right? And that is what you want to do for every sum, but this is only possible in the principle of mathematical induction, where you're given this magic wand and you can say that let Pm be true, right? So let's go ahead and do this step. Here in this case, like you know that you have here Pm to be that statement which has to be a multiple of 24, right? So we will now write this, that is, we have here 2 times of 7 raised to the power m plus 3 times of 5 raised to the power m minus 5, right? And you will say is divisible by 24, right? And obviously this is by assumption, so you don't have to prove this, right? Okay, so as we have this step, now we come over to the third step, which is the proving step. So when we come to the third step, we say proving Pm plus 1, Now in order to prove Pm plus 1, here in the last step, wherever there is m, we just have to substitute m plus 1, right? And using the last step, we have to prove this. So as such, if you talk about writing the step, it is pretty simple. You just have to write 2 times of 7 raised to the power m plus 1, to which is to be added plus 3 times of 5 raised to the power m plus 1, and from which is to be subtracted 5, right? Now here guys, as if we bring it to some form of what we had in the last step, proving this will become pretty simple. And for that here, I like you people to do one thing, that is you can write from the last step that this implies to 2 times of 7 raised to the power m is equal to, or rather what you can say that plus 3 times of 5 raised to the power m minus 5 to be equal to, say, some 24k, as this has been considered to be a multiple of 24. So obviously it will be equal to some 24k. Here you can say for every, this sign is actually the sign of for every k to be an element of integers, right? Okay, I, that is capital I, represents here the set of integers. Now guys, from this you can now say that if you talk about 2 into 7 raised to the power m, that can become equal to 24k, right? From which you subtract the other terms, that is 3 times of 5 raised to the power m plus 5, right? So this, guys, let's say becomes your equation number 1, which in times to come you can substitute in proving Pm plus 1. So when we go ahead to this next step, we can now write this as 2 times of 7 raised to the power m, which is multiplied by 7, and to that is added plus 3 times of 5 raised to the power m plus 1 minus 5. Now guys, as here we have 7 raised to the power m, right, into 2, which had a value given by equation number 1, that we can substitute here. So in place of this 2 times of 7 raised to the power m, now we're going to keep its value as 24k minus 3 times of 5 raised to the power m plus 5, and that, guys, is multiplied with 7. Next then we talk about the next 2 terms, that is plus 3 into 5 raised to the power m plus 1 minus 5, right? Now guys, here on a multiplication we find that we can write this to be 24 times of 7k, because we've got to show that this is a multiple of 24, so obviously each of the terms should be divisible by 24. Next then we write this to be minus 3 into 7 times of 5 raised to the power m and plus 35, and plus we have 3 times of 5 raised to the power m plus 1, from which 5 is subtracted. Now guys, here we have some like terms, so we're going to solve out the like terms, that is the terms which are with 5 raised to the power m. So we can write that as 24 times of 7k minus, we have 3 into 7 is 21 times of 5 raised to the power m, right? And plus we have here 5 which can be taken out. As such, we can write this as 3 into 5, right, which is further multiplied with 5 raised to the power m, right? And to that is to be added 35 minus 5, which is 30. Next, now you can write this as 24 times of 7k, right? From which now here we will be taking 5 raised to the power m to be common outside. As such, here we have 21 minus 15 and plus 30, right? Now guys, this becomes a trinomial where we have 24 times of 7k minus 5 raised to the power m still stays outside, and inside we have here 6, right? And further we have here 30, which can also be written as 6 into 5, right? And thus what you can do is you can take the 6 to be common outside, and thus you can write this to be 24 times of 7k minus 6 can be taken common out of the both of these terms, and then you have 5 raised to the power m, right, minus 5, which is left here. Right now guys, as you cannot further prove this to be a multiple of 4, that is this expression which is 5 raised to the power m minus 5. So next what you require to do is you require to prove this to be a multiple of 4, And if you can do so, 6 is already out here. So again, this term will also be a multiple of 24. So let's go ahead and do it. That is, now guys, the important thing is to prove 5 raised to the power m minus 5 is a multiple of 4, right? Now guys, in order to do this, what we do next is we again go through the grind, that is the 3 steps. Now we call in the first step, which is the basic step. Now if you remember, when we talk about the basic step, we talk about n to be 1, right? So here guys, we'll be talking about p1, right? And if you talk about p1, then you will get it to be here as 5 raised to the power 1 minus 5, right? 5 raised to the power 1 is 5 minus 5. You will have that to be 0. You can say that this is divisible by 5, right? And that is so because if you talk about dividing 0 by 5, you will find that there is no remainder which is left, and as there is no remainder which is left, thus you can say that it is divisible by 5, right? And this is what we primarily need to check when we find that a number is to be divisible by another number. There shouldn't be any remainder which should be left, right? So guys, now we come to the second step, which is now the induction step. And when we talk about the induction step, then in the induction step guys, we will now consider, let's say, some p of g, right, to be true, right? And if say this p of say g is true, right, then now we can write this, that is, we will have this to be 5 raised to the power g minus 5, right, is divisible by 4, right? And if it is divisible by 4, then further this implies that 5 raised to the power g minus 5 will become equal to some 4 times of, say, some f, right? As such, here we will have 5 raised to the power g will become equal to 4 times of f plus 5, right? Now guys, in times to come, in the third step, you're going to use this so that we can prove p of g plus 1, right? We are not using m because m has already been used in the last part of the sum, right? So here now guys, we talk about the statement p g plus 1, and when we do so here, we will now have to prove that this 5 raised to the power g plus 1 minus 5, right, is divisible by 4, right? And we have to prove this, right? So further, when we have to prove this, then we can write proving this. And now guys, if you talk about 5 raised to the power g plus 1, we can write that as 5 raised to the power g, which is multiplied with 5, from which 5 is subtracted. Now since you find that 5 is common to both of these terms, so we can write this as 5 times of 5 raised to the power g minus 1, right? And now guys, here what you can do is, if you keep the value of 5 raised to the power g here from, say, equation number 2, right, we can write it to be 5 times of the value of 5 raised to the power g is 4f plus 5, right? And now guys, here what you can do is, if I'm sorry, here not plus 5, and then further after that you also have here except the value of 5g also minus 1, right? So further guys, this can be written as 5 times of 4f plus 5 minus 1 is 4, right? Now guys, out of these two terms, we find that 4 is common, so we will have 4 which will be multiplied with 5, and within here we have f plus 1, right? So therefore we get to see that if you talk about p of g plus 1, right, is divisible by 4, right? And this we can say marked to be say some entity number 3, right, which we can substitute in the earlier proof, right? And then we can continue with the earlier proof where we have 24 times of 7k, right? So we'll mark an asterisk here so that we don't get lost, rather 3 musketeers, right? And we'll make the 3 musketeers down below here. That is, this is the proof of that. Now, before we talk about these 3 musketeers, one quintessential statement is required that I'll make you people write always at the end of every sum. That is, since g plus 1 is an element of integers, therefore for every g to be an element of integers, right, pg is always true, right guys? So here, as g plus 1 is any number from the set of integers, thus for any g this is always going to be true, right? And this is a statement which you require to write at the end of every sum of the principle of mathematical induction. Now guys, here we will be writing the final step, that is using the 3 musketeers, the 3 asterisks. Now we'll get to our basic step, that is 24 times of 7k. So we have 24 times of 7k, and the rest is minus 6 times of 5m minus 5, right? And as this 5m minus 5 has now become a multiple of 4, right? So you can write this as 24 times of 7k minus 6 times of 4 times of, say, some s, right, where s is an element of integers. So as you see here, you can write this further as 24 times of 7k, which is further multiplied, from which is subtracted 24 times of s, right? And here, as you can take 24 to be common all through, so inside guys we are left out with 7k minus s, right? And therefore you can say that the statement pm plus 1, right, is always true, right? And here then finally you will write the quintessential statement that since m plus 1 is an element of integers, therefore for every n is an element of integers, Pn is always true, right? So this is, guys, what we had in this sum. Now I'll just quickly explain this all over so that if there is any doubt which is withstanding, all of that gets removed. Now in this question, guys, we've been given that we have to prove a mathematical statement by using the principle of mathematical induction, and that statement is 2 times of 7 raised to the power n plus 3 times of 5 raised to the power n minus 5 is divisible by 24 for all n to be an element of natural numbers. Now here, guys, first we do the basic step. That is, the basic step is we put n to be 1 here. So here we talk about the statement P1. So when we keep in place of n1, we have 2 times of 7 raised to the power 1 plus 3 times of 5 raised to the power 1 minus 5. Now 2 into 7 is 14, 3 into 5 is 15, 15 and 14 make it 29, from which if you subtract 5 you will get 24, and obviously then this statement P1 becomes to be a divisible of 20, to be a multiple of 24, or is divisible by 24 if you keep 24 in the denominator, then on the division you do not get any remainder. As such, you can say that this statement P1, or this expression P1, is divisible by 24. Now next we come to the induction step, where we have to consider that using the magic wand we are going to say that let Pm be true, and it will stand to be true. And then what we do is, wherever we have n in the statement Pn, in place of it we keep n, right? And on keeping m, then what we do is we write that to be equal to some 24k, as it has been considered to be true, right? And further then, one of the difficult entities, that is 2 into 7 raised to the power m, can be written as, by making it the subject of the equation, as 24k minus 3 times of 5 raised to the power m. This dot symbolifies multiplication, right? And minus 5 taken to the other side is going to become equal to plus 5, right? So further, guys, here we have the value of 2 times of 7 raised to the power m. If you wanted, you could have even made 3 times of 5 raised to the power m to be the subject of the equation, as this is an equally problematic term, right? Next, now we have to prove Pm plus 1, where what you do is, in place of m, now we'll be substituting m plus 1, right? As such, now we have 2 times of 7 raised to the power m plus 1 plus 3 times of 5 raised to the power m plus 1 minus 5. That is, wherever there was m, just m plus 1 has been replaced with it. Next, now, as we have what we took as true, 2 into 7 raised to the power m to be the subject of the equation. So we will try and convert 7 raised to the power m plus 1 in the form of 7 raised to the power m. So here, children, I'll quickly remind you a rule which you learned in indices. That is, if you have a raised to the power m which is multiplied with a raised to the power n, then that gives you a raised to the power m plus n. So here we've just done the reverse. That is, we have a raised to the power m plus n, and we've written it to be a raised to the power m multiplied with a raised to the power n, right? And thus here 7 raised to the power m plus 1 can be written as 7 raised to the power m, which is multiplied with 7. Now, guys, here next what we do is we talk about the terms which are of 7 raised to the power m to be now written as what we have the value in the expression 1. So 2 times of 7 raised to the power m is replaced by 24k minus 3 times of 5 raised to the power m plus 5. And as to that, 7 is multiplied here, so we'll further multiply that by 7, and then we will write the rest of the 2 terms. Now, after multiplying 7 within, we find that the first term has 24, so we'll keep this 24 outside, and then we will have 7k inside, which shows that the first term is a multiple of 24. Now, our task is to prove the rest of the 4 terms also to be a multiple of 4, and since in the next 4 we find 2 pairs of like terms, so we deal with the like terms. Now, this term, which is 5 raised to the power m plus 1 containing, can be written as 5 times of 5 raised to the power m plus 1, like we discussed in the last step of 7 raised to the power m plus 1. Then we can write this as minus 3 times of 7 times of 5 raised to the power m and 3 times of 5 times of 5 raised to the power m. Then in both of these terms we have 5 raised to the power m, which can be taken common outside along with the minus sign, and then we are left out with 21 minus 3 to 5, which is 15, and then the 2 like terms 35 and 5 also get simplified and become 30. Now, when you do a subtraction of both of these terms, you find that that comes to 6, right? And as such, 6 being common in the last 2 terms, you can take this 6 to be common outside, and then you have 5 raised to the power m minus 5 inside, which you can not prove to be a multiple of 4 easily unless you use 5 raised to the power m minus 5 to be proved to be a multiple of 4 again by using the principle of mathematical induction. So again, we come in the recluse of this principle and we go through the basic step where in place of m we substitute 1. As such, we have it to be 5 raised to the power 1 minus 5, which becomes equal to 5 minus 5, that is 0, and it is divisible by 5 because if you divide this by 4, I'm sorry, this is not divisible by 5, but it is to be, obviously it's divisible by 5 because 0 will be divisible by any number. But here, guys, as we require this to be divisible by 4, right? So as such here, what we are going to do is we will now be writing this to be divisible by 4. Right? And why is this divisible by 4? Because if you divide this by 4, then there's not going to be any remainder which is going to be left. And that is what we require to check whether any number is divisible by another number or not. That is, no remainder should be left, right? After this, now, guys, we talk about the next step, which is the induction step. And using the magic wand, you just say that let P of G to be true. That means we talk about the statement P, where in place of N now we have G here, right? So if we talk about this now, we go ahead by here just writing 5 raised to the power g minus 5 from the statement Pn, right, to be divisible by 4. And if this is divisible by 4, obviously this can be written to be equal to 4 times of some f, where f is an element of integers. Next, now we will also write this so that the teacher is in no confusion as to you do not know the value of what f is. So here you will say that for every f is an element of integers, and here also it will be best if we write this statement Pn that we have to prove, which is 5 raised to the power n minus 5 is divisible by 4, right? Now next, continuing guys, after having the value of 5 raised to the power g to be 4f plus 5, now when we talk about pg plus 1, when required we can keep the value of 5 raised to the power g. So as here we have 5 raised to the power g plus 1 minus 5, out of both of these we take 5 to be common outside, and then we have 5 raised to the power g inside, whose value can be kept to be 4f plus 5. And when we keep it to be 4f plus 5, and from that if we subtract 1, right, we get 4f plus 4. From both of these terms we can take the 4 to be common outside, and when we do so we have 4 into 5 outside, and inside we have f plus 1. And since here f is an element of integers, so you will say that pg plus 1 is divisible by 4, right? Since if you talk about g plus 1, it is an element of integers, therefore for every g to be an element of integers, and here you can also talk about n, right, also to be an element of integers, pg, or rather you can say that Pn is always going to be true, right? Because here primarily with what we are interested is we are interested with Pn, right? So here guys, what we'll do is we will write this to be Pn. So we will thus here say that Pn is always true. Now after we prove that Pn is a multiple of 4, so we now take this to the last step where we were stumbled by this expression 5 raised to the power m minus 5, and now we can say it is a multiple of 4. So from here we continue, that is the statement Pn plus 1, this part which we were awaiting to be a multiple of 4 is what we can write now. As such, we can now say 24 times of 7k minus 6 times of 5 raised to the power m minus 5 can be now written as some 4s, and here you can even write this, that for every s to be an element of integers, right? And then further here 4 into 6 is going to become equal to 24. As such, 24 can be taken common out of this binomial, and then you will have 7k minus s inside, and then further you can say that therefore Pm plus 1 is always true, right? And here as Pm plus 1 is always true, m plus 1 being from the set of integers, therefore for every n to be an element of integers, we can say that Pn is always going to be true. So clear with this sum guys? Was this not a daunting sum? That is a challenging sum. And all those people who've been able to do it in the single go in the comment section, do write yes, done. And all the other people, wait for the other sums. I'm sure probably the other sums which come your way in the lectures to come, you'll probably be able to crack it. But whatever sum be it, always take a little time out so that you can give it a try. I can assure you that that increases your confidence as well as your intelligence, because in accordance with what knowledge you should have had, you already have it and you just have to apply it. You just have to get yourself out from the scare of your shell that you won't be able to do the sum. Give it a try, right? Gradually you'll get to see that you will do many positive things, and then you'll be able to crack complex sums, right? So that's all for now guys, signing off now. Bye for now, have a nice time, enjoy your lives. Bye guys, bye.